3.3 is going to ask us to list all the possible rational zeros of a given polynomial. And this is the rational zero theorem, and it looks a little bit more scary than it actually is. Basically, they're telling us we have a polynomial function. So if you have a polynomial function of unknown degree, you can't really write out what it looks like. So something x squared plus something x plus constant is a polynomial function. Something x cubed plus something x squared plus something x plus a constant is a polynomial function. So they can keep on adding a term. So what they've got here is the first term is some number x to a power, the highest power, then one lesser power, and so on until we get down to x to the first and a constant. So basically we have a polynomial of unknown degree, but it has a highest power term and it has a constant. Those are the things that we care about. So it has to have integer coefficients, so it can't have like 7/3 or 1.57 or pi as a coefficient. It's got to have integer coefficients. And P over Q is a rational zero. So rational, if you focus on that word, rational means that we have like a regular fraction or a whole number or an integer, positive, negative. And a zero means that it makes the polynomial's value equal to 0. So if we have a rational zero, like 2/3 might be an answer, or 1/2, or 5, or -7, or 17. It should be a rational zero if this is true. So P over Q is the structure of the rational zero. P is a factor of the constant term. P is a factor of a sub 0. And Q is a factor of a sub n, the lead coefficient. All right. Factor of, meaning that if we listed all the factors, like for example, 6 divides by 1, 2, 3, 4, and 6. So that'd be the factors of 6. And plus or minus each of those. 10, 1, 2, 5, and 10, plus or minus each of those. So the factors of, we're listing all the factors of the numbers. All right? So we can go from infinity possible answers into, maybe 20 possible answers to a problem that are rational. So that's what example 1 is. We're going to use that theorem. So use the rational zero theorem to list all possible rational zeros of this. So all possible. That doesn't mean they're answers, it means they're possibly answers. What we're doing is we're making a list to perform guess and check with. So we don't have to guess and check infinity numbers, we don't have to guess and check 20 numbers, or hopefully 5 or 10 numbers. So if I'm going to use the rational zero theorem, whenever it says to do this, I want to focus specifically on the lead term and the constant. Those are the only two numbers that matter. Every other power of x does not have any effect on the rational zeros, just those two numbers. I want to list P, which is all the factors of 12, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. 5 doesn't go into 12, plus or minus 6, 7, 8, 9, 10, 11 don't go into 12, and plus or minus 12. Okay, so we list every single number that divides into 12, put a plus or minus in front of it. Okay, Q is all the factors of 4. I'm not going to put pluses and minuses in front of these, I'm just going to put the numbers. So the only numbers divided into 4 are 1, 2, and 4. The reason I'm not going to put plus or minus, I've already dealt with that with P. That'll deal with the plus or minus. That'll get my mind wrapped around the fact that I got to put plus or minus on my answers. All right? But plus or minus 1 over 1 is plus or minus 1. Plus or minus 2 over 1 is plus or minus 2. So you don't have to put plus or minus in both of them. All right? So, and all we have to do here is list all the possible rational zeros. So the possible rational, I usually call roots, so PRR. If you want to go PRZ, that's fine too. Possible rational answers are going to be plus or minus every one of these P's over every one of these Q's. All right? So basically, divide by 1, you get the whole list of P, right? So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. If I take each of those numbers divided by 2 and reduce, I'm going to get plus or minus 1/2. Right, 1/2. 2 halves is equal to 1, we already have that. 3 halves we don't have yet, so plus or minus 3 halves. Plus or minus 4 halves equals 2, we already have. Plus or minus 6 halves is 3, we already have that. Plus or minus 12 halves equals 6, we already have that. You don't have to list them more than once. All right. Next we have all these numbers divided by 4, so I get plus or minus 1/4. Plus or minus 2/4, better known as a half, we already have it. Plus or minus 3/4. Plus or minus 4/4 is 1, 6/4 is 3/2, 12/4 is 3. So there's my entire list there. So of all the infinity answers the original problem could have had, now we're down to 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 possible answers that are rational solutions to this problem. It is a fourth degree polynomial. The next step is what we're going to be doing in the next I think of the very last example today. The next step here would be to determine if any of these answers actually work. We can perform synthetic division then to reduce it down to a quadratic, and then with the quadratic we can get all the answers. So it's a way of finding all the answers. As long as you have some rational answers, you can reduce the polynomial down with the answers till you get down to a level you know how to do with the quadratic form.